My presentation today is robotic cilia metasurfaces for programmable microfluidic manipulation. At first, we know that there are many existing methods to do the actuation for artificial cilia. For example, we can use pressure to do the actuation. We can also use some electrostatic force to do the actuation. We can also use the magnetic actuation to make the artificial cilia. However, all these actuation methods have their own limitations. For example, the pressure-driven one cannot be made into microscale. The electrostatic force needs a large actuation voltage, which limits its application. And the magnetic actuation one cannot, it's hard to achieve local actuation. Mm. Based on these considerations, we think it's necessary to make some new actuation methods that can overcome some of these limits. We choose the electrical actuation method to make our artificial cilia. The actuation mechanism is based on the electrochemical reaction of platinum. For, at first, we make our cilia using two layers of metal materials. The first layer is platinum, the second layer is titanium. When we apply a positive voltage about 1 volt, the platinum surface will be oxidized. This oxidation will expand the surface. And when we apply a negative voltage, for example, negative zero point 0.2 volt, the oxidized platinum surface will be reduced. So we can apply AC voltage to do this actuation again and again. And the right image shows you the SEM images of these fabricated artificial cilia, and the bottom right set is the is the TM image of this cross section. Next, I want to show you how we measure the pumping performance. As you can see in the right video, we have one array of these artificial cilia. Then we do the actuation, and in the meantime, we put a lot of microscale particles in the fluid. Then we measure the velocity of these microscale particles to let this velocity represent the pumping velocity of this artificial cilia. The right image shows you the relationship between the pumping velocity and the frequency for different lengths of artificial cilia. As you can see that the maximum pumping velocity is about 60 micrometer per second, and for most of these artificial cilia, it can reach a best pumping velocity at tens of hertz. Mm, the next one, I want to show you the pumping mechanism of this artificial cilia because we are using like bending and unbending. Why this thing can give us non-symmetric trajectories, because in microscale we have to have non-symmetric trajectory in order to have some pumping. To do this, we plot the trajectory of this cilia in one loop. As you can see, that the tip actually forms some closed area, which indicates the non-symmetric trajectory. The reason behind this is that when we look at the positions that is close to the tip of this artificial cilia, it withstands less fluid force and it behaves more rigid, which means when we have some actuation, it's easier for the tip to do this actuation than the root. So when one actuation comes, the actuation will propagate from the tip to the root. This propagation breaks the symmetry of this of the trajectory. To validate this, we also did a simulation using the resistive force theory. As you can see here, the trajectory from the simulation consists very well with the experimental results. And having known that we can do pumping for our artificial cilia, what we can do is to generate some cilia units which has several cilia arrays and selectively actuate some of them to get some flow geometries. For example, here, as you can see, we can actuate 4 arrays of this unit, which consists of 8 cilia arrays. And we can get an extensional flow. The flow goes in from the bottom and top, goes out from the left and the right. The yellow lines indicates the fluorescent particles we put in. We also have a video to validate this. You can see the motion of these fluorescent particles. And we also did a simulation using the Stokes lead to simulate one cilia to get the whole 3D velocity profile. As you can see here, we have our experimental results in the bottom and the 3D simulation in the middle and the average simulation result at the top. Apart from the extension, we also did some other flow geometries like flow expansion, flow transportation, flow turning. And having known that we can have these basic flow geometries, what we can do is to combine these flow geometries to get some more complex flows. What you see here is a 64 independently controlled cilia arrays. We call it cilia matrix surface. We can use this matrix surface to selectively actuate some of these arrays to get the flow patterns we want. And how we do the actuation? Here I use LabVIEW to generate the voltage signals, and the voltage signals are then sent to the data acquisition device, which is connected to the chip carrier of our matrix surface. Okay, so in this case, we can use our computer to do this actuation. Here I show you several examples of the flow patterns we can get. The first one is two independently flow trajectories. I also plot the trajectory of two represent particles, one for each, as you can see here. We also did a simulation to do this to compare with our experimental results. Apart from this flow pattern, we also did some other patterns like flow rotation, flow transportation, and one flow diverges and merges again. Here, the advantage of this method is that we can switch from different flow patterns. A simple demonstration here is that we can change the rotation direction of the rotation flow. As you can see, at first we get a clockwise rotation, then we change the actuation, we get a counterclockwise rotation. All these previous actuations are tethered actuation. Here, we want to do more, to do some untethered actuation. We choose to use some tiny solar cells to transfer the optic power into the electrical power. Also, in order to get some complex controls, we designed some CMOS circuits to help us. As you can see here in the right image, we have the power for the solar cell for our actuator and the cell for our circuits, and also the different components of the circuits. What we can get from this circuit is that when we shine light to this power, to this circuit, the circuit can give us 8 oscillating signals with pi/4 phase delays. That's basically what we want to get. The right image is the block diagram of the circuit. So after we do this fabrication, what we can get is the circuit at one side, and then we wire out some of the contacts to some specific cilia arrays. When we release this thing and do the actuation, what we can get is the adjacent arrays with some phase delays. What we can do is to check the velocity of these particles and measure this velocity. So here I also show you a plot with the relationship between the pumping velocity and the phase delays. As you can see that the pi/2 phase delay gives us the best pumping velocity, which is also consistent with the previous literatures of metacoronal actuation. Finally, I want to thank you all the people who made contributions to this work and all the funding agencies who supported us. And this paper has been accepted by Nature recently.